let me just open the presentation by saying that there are many different kinds of sensors, many different ways to distinguish sensors. One way is, how much does it cost? How much power does it consume? And of course, those kinds of constraints really tend to dictate whether it can fit in a given application or not. But then, what does it do? Is it a one-dimensional sensor, two-dimensional sensor? Is it visible light? Is it infrared light? Lots of choices in this regard. And the choice of a sensor has enormous implications on what the system can do, what information is being captured visually, and what kinds of algorithms and how much processing power and memory bandwidth and so on are going to be required to do those things. So the purpose of this presentation is to give you a sort of a quick tour through some of the major existing and emerging sensor technologies and some of the trade-offs associated with them. So with that, let me turn it over to Eric.
Okay, so embedded computer vision with 2D sensors uses complex software to derive information from an image. So, it's interesting, everyone here, we were used to using algorithms. We've talked about algorithms all day. One of the things, think about what other technologies we use where we only talk about the software but not talk about the hardware. And by hardware, I mean the actual input device. We've assumed for computer vision, we've assumed 2D sensors all along. I mean, throughout the whole discussion today, it's been almost always 2D sensors. So but that's not the case in other situations. So in this conversation, in this presentation, we're going to start out talking about 2D sensors, some of the advantages and disadvantages. Then we're going to start talking about 3D sensors, because 3D sensors are starting to come down in cost now where they're worthwhile to look into. So this algorithm here, this is an example of an algorithm you'd implement with a 2D sensor. It's actually a pedestrian detector. You got the monochrome image, and then you're going to go ahead and you're going to pull the edges. You're going to pull off the edges, and then you're going to go ahead and do a contour, and then you're going to segment it out. Well, think about how much easier that would be to do that algorithm if you had a 3D sensor as opposed to a 2D sensor. The computer has to do all that based on strictly on luminance differences. Whereas if you give it a 3D sensor, now you've given it all this additional information. So I guess the core point there is that when you're evaluating a vision algorithm, maybe it's about time that we also evaluate the sensor that we're going to use for the vision algorithm, as opposed to just assuming it's going to be a camera. So what does a 2D sensor do? A standard 2D sensor captures a 3D scene and converts it into a 2D image. And during that process, information is lost. And that information has to be recalculated or recaptured via an algorithm. 2D sensors are relatively low cost and very common. That's why we use them. But that's changing. You can think of a computer vision design with a 2D sensor sort of as a graph, where you've got the low cost of the sensor, but the high cost of the software to extract the information from the sensor. Well, as you go up in price of sensor, for instance, a 3D sensor, or maybe an IR sensor, an IR sensitive sensor for people detector, the sensor price starts to go up, but the software starts to get simpler. So in designing an embedded system, embedded vision system, the cost and the type of sensor can become a large factor. In terms of 2D sensors that are available, you've got CCD and CMOS. Those are the two most popular. Now CCD, we probably don't use very much in this room because of the expense. CCD sensors are significantly more sensitive. They're used quite a bit in the scientific community, a lot in astronomy. The reason they're more sensitive is if you look at the squares there, you can see each one of those squares is a pixel. The actual light capturing portion of the pixel is very large in a CCD, relatively speaking. And that is what makes it. So the actual signal, the actual light that it converts into signal is very high. The other advantage of a CCD is if you look down in the lower corner, there's an amplifier. Actually, let me just walk down here without killing myself. There's an amplifier right here. There's one amplifier for all the pixels. What's nice about that is that it's a consistent noise. So each pixel in the CCD has a consistent noise parameter to it, which can be easily factored out later on. And you'll see that's not the case in the CMOS sensor. CCD sensors are also significantly more sensitive to UV and ultraviolet, or I'm sorry, UV and IR. Now the CMOS sensor, one of the things you'll notice right away with this diagram is if you look at the box, each one of those green, blue, pink boxes represent a pixel, and what's the box that says PD, that's the actual photodiode. Now what you'll notice is that's only about 1/3 of the surface area of the pixel. So in a CMOS sensor, each pixel only picks up about 1/3, it's anywhere from 25% to 1/3 of the light. The rest of the pixel area is actually transistors. Because whereas in the last slide, whereas the CCD had only one output amplifier, the CMOS has one amplifier per pixel. And each one of those amplifiers takes anywhere from 3 to 5 transistors. And that takes up area, actually area of the pixel. The net result is that because of that reason, the CMOS sensor is actually less sensitive. You actually get less of a signal for an equivalent amount of light. Now the advantage of CMOS is it's cheap. It's a very inexpensive process, and relatively speaking, they are significantly less expensive. The other advantage is they're low power with the CMOS process. Now the disadvantage is, remember before I said with one amplifier, you got this one noise pattern that you can easily filter out. With CMOS, each one of those amplifiers has its own unique noise characteristics. So filtering it out becomes significantly more difficult. Now Sony recently has fixed a lot of these problems and has really brought a game-changing technology to the field. It's referred to as a backside or a backlit CMOS sensor. And what they do now is if you look here, okay, so there's your traditional CMOS sensor. I'm from the south side of Chicago, so I'm pretty loud, so I don't think I need an amp. But this is your traditional CMOS sensor, and you can see the metal layers blocking the light. So here's my light coming in, and it's blocking the light. And here's my photodiode down here. Photodiode's not getting that much light. What Sony's done is they put the photodiode on the back of the sensor. So now the photodiode gets all the light, okay, and all the electronics are on the front side. It's called a backlit sensor. This sensor is a game changer. They're reporting, and I put that in quotes because that's right out of their press release. They're reporting a plus 8 dB signal to noise ratio increase. They're also, if you happen to have the iPhone 4S, you'll know, or if you've read the reviews, the camera in that particular phone has gotten great reviews. I mean, just phenomenal reviews. That is a 5 megapixel backside lit camera. So this is game-changing technology. This is definitely something to keep an eye out for. All the advantages of CMOS with the sensitivity of CCD. And finally, this is more about packaging than anything else. Very rarely in what we do here are you going to go out and buy a CCD by itself or a CMOS sensor by itself. In most cases, you're going to buy it in an enclosure. You're going to buy it as a chip cam. What happens here is the manufacturer of these chip cam, OmniVision's big one, they take the sensor, the CMOS array, they combine it with an image sensor processor, and they actually produce a final unit for you. And this is really important in CMOS because even the Sony sensor, remember, it still has all those amplifiers, and all those gains need to be compensated for. So one of the things that this gives you is, like I used to write drivers for these types of cameras, and one of the things you'll get is when you buy these cameras, you'll actually get a list of thousands of constants, and those constants are actually gain compensations to make all those pixels equal, to equalize the gain between pixels. So when you first initialize the sensor, you send all those constants to make everything equal. Okay, Shehrzad.
Thanks, Eric. Can you guys hear me? Great. So now we're going to move on from 2D to 3D, and the third dimension is not time, but it's actually depth. So historically, 3D sensors were kind of considered a exotic technology, a niche technology. They were expensive, maybe not so robust, but the Xbox Kinect has really changed that, and it's brought the technology into the living room and has really popularized 3D sensing. So in this section, we're going to cover 3 different types of 3D sensors. But before we do that, I just wanted to just go over describe what the output of a 3D sensor actually is. And primarily, it's a depth map. And we have an illustrative example here. This is an actual image generated by the Kinect. Now, in a traditional 2D image, like the kind generated by the CMOS or CCD cameras, sensors that Eric just described, each pixel actually is, its intensity is mapped to the amount of light that it actually measured, versus a 3D sensor where each pixel is proportional to the depth from the object to the sensor. So in this image, it's been color-coded such that the red pixels are closer to the sensor, and as you move progressively further and further back, it's yellow until it's blue, the background. Now you'll notice that there's some black, and there's a few reasons for that. First of all, the Kinect can only measure distances past 19 inches. So the stuff on the bottom there is a shelf or something that was too close to the sensor for it to measure the distance. And then you'll also notice there's this kind of like a halo over part of it, but behind the guy's hand and the head and arm and shoulder. And this is a common problem in 3D sensing technologies. There's occlusion and there's other ambiguities that a lot of times these sensors can't resolve. So the processing system behind it is able to figure that out and will just put no data in there. So the first type of 3D sensor that we'll talk about is 3D via structured lighting. And the concept behind structured lighting is we're going to throw out a predefined pattern onto the scene, and then we're going to image that scene, and then depending on how that pattern looks to us, we can, this processing system can ascertain how far away the object is. So the sensors, based on this method, they use a projector, and they project a known pattern, and the camera senses the result. This is an example of Xbox Kinect, so you can see this is the structured light, it throws out a dot pattern. Now the Kinect in particular uses an astigmatic lens with different focal lengths in the X and the Y direction, and it actually projects an image of a bunch of dots, as you saw in the previous slide. They change their shape and their orientation depending on how far away the object is from the lens. And because of the fact that the lens is actually astigmatic, circles actually show up as ellipses, and then the orientation of each of those ellipses is proportional to the depth. So the processing system behind the Kinect can actually make sense of all these rotated and oriented ellipses. What are some of the advantages and disadvantages of this? Well, some of the advantages include simpler processing and a lower cost processing. You can get high resolution and they're accurate. Now the downside to these are there are issues doing this outdoors and in sunlight or with a lot of ambient light. And also power. This is a projector, so that can consume a lot of power. And you also need a custom lens for the projector. So the next type of 3D sensor is stereo. And the principles behind stereo have been around for over a century. And the basic concept is to use triangulation. We use two sensors, and we use triangulation to infer the depth from the same image that's imaged from two slightly different vantage points. And you can kind of get a sense of how this works is if you focus your eye on an object and cover one eye, and then move your hand to the other eye, you'll notice that there's a kind of a lateral shift. And that lateral shift is actually how your brain measures depth. And it's the same concept in stereo triangulation. And there's an example here where there's a 3D point, XYZ, that gets projected onto a left camera, XL, and a right camera, XR, YR. And the delta in X is actually proportional to the depth. And in fact, the same concept is used in 3D movies. So the way those work, you wear those glasses, and typically the left eye will be a red lens, and the right eye will be a blue lens. And each of the pictures are actually, the red picture and the blue picture are offset just a little bit, so that when you put the glasses on, your brain kind of fuses it together and you get that 3D effect. 3D stereoscopic vision is used in a bunch of different applications, robotics, military, industrial machine vision, surveillance. And there's two types of this type of 3D sensor. They can either be discrete or integrated. And I'll cover discrete binocular stereo first. So here are three different examples across three application domains. The Point Grey Bumblebee is, Point Grey is a company based out of Vancouver. This is a binocular stereo system that's used in robotics and machine vision. When you buy it from them, it's already comes calibrated and will generate a 3D depth map for you. A digital camera, I think there's about 4 or 5 of these. These are digital stereo cameras. There's 2 lenses. This is one by Fuji. And then this really cheap, kind of funny looking Japanese 3D webcam called the Monero. And one of the interesting applications for the webcam is actually online retailing of all things. So there's currently a website right now where they actually ask you to put a CD around your belt buckle. They know how wide the CD is, and then it can measure your waist size. But you can imagine if you had 3D, you know, turn around, you can get a really nice tailored fit. So that's one of the interesting uses for the 3D webcam. So as opposed to discrete binocular sensors, there's also dual stereoscopic sensors where the 2 sensors are integrated. And you combine 2 image sensors into one system on a chip, and you output a combined stream over a single bus. So some of the advantages of that are the packaging, obviously, and also you get a lot of nice combined control versus basically bolting 2 cameras together, as you saw in the previous slide. The analogy here is if I take 2 motorcycles and link them together with 2 axles, I don't get a car. And the synchronization between 2 cameras is actually pretty important because the pictures need to be taken at the same time in order to get a really accurate and robust 3D measurement. Yes?
Is there a minimum distance between the 2 cameras in order to be able to get that 3D parallax?
Yes, exactly. Exactly. And you can play around with that a little bit depending on what you want your depth of field to be. So there's always going to be some blind spot depending on how you set it up.
If you make this one module, that would be kind of constrained in terms of that separation, wouldn't it?
Well, yes, but once you actually design a stereo system, the baseline, the difference between that defines that parallax geometry is set in stone. So you're not going to be changing that. So basically your lenses and everything are all derived from how far apart they are.
Typically, how far apart are the lenses in these integrated?
1 centimeter, 1 to 3 centimeters. They're pretty. I mean,
And that's enough for the stereoscopic effect to work.
over a limited range, yes, and you'll find that on the. I think there's an HTC phone, right? Yeah, HTC phone. Yeah.
LG and HTC.
Right. So you get better frame synchronization on an integrated system, which means that I can usually accommodate faster motion. And also, the more tighter integration leads to better calibration, which in turn leads to better stereo. 2 examples, I don't have pictures of these, but Lattice and Aptina actually announced at CES in January stereo camera reference design, and then Medusa MK1 is a British company. So the last type of 3D sensor are time-of-flight cameras. These are imaging devices that consist of 3 elements, the image sensor, the lens, and then an illumination source. And there's a diagram here that illustrates how this works. So the general idea is you throw out some light, and it strikes the object and comes back, and the imaging system measures that time, and the time it takes for it to sense how long that light took to bounce and come back is proportional to the depth. So, and some of the applications that these are used in, very common in automotive for pedestrian detection and driver assistance, prevalent in robotics, and have a long and storied history in military and defense and aerospace. The illumination source is usually either one of 2 types. It's either a pulsed laser beam or a modulated beam. And the type of beam is dependent on the type of actual sensor, the time-of-flight sensor. There are sensors with digital time counters that are used with the pulse laser beams. Also, there are range-gated sensors that have a shutter that open and close at the same rate at which the pulse beam is going out, so that the amount of light each pixel sees is proportional to the depth. And then there's also sensors that are actually phase detectors. These use a modulated light beam whose strength is varied over time, and so they have a phase detector, and so they measure the phase of the incoming light, which in turn is proportional to the time of flight. So you derive the time of flight indirectly. So what are the pros and cons of 3D time of flight cameras? Oops. The image processing underlying all of this is much simpler than stereo. And because it's so simple, it's probably more suitable for real time. But because of background light and also multiple reflections, that means that the processing can't be too simple. But nevertheless, the frame rates can be very high, easily upwards of 60, 100 frames per second, which is difficult to achieve with traditional stereo. The resolution, however, is usually lower than stereo. One interesting concept to consider is sensor fusion, where actually you can augment stereo with time of flight. Some people do that. And there's a couple three examples here of time of flight cameras out there in the market: Phototonic, Mesa, and Soft Kinetic. And actually, there is out there in the demo, there's PMD Phototonics, which at this year's CES announced the first commercially available 3D time of flight sensor. And last year, OMEC and PMD announced a partnership to deliver high-end gesture recognition based on these based on their respective technologies.
Hey, Shehrzad, just a question.
Yes.
What kind of resolutions do you get on these cameras?
Well, that's I mean, it depends on how far you're willing to scan. I don't have a number off the top of my head. I can get that for you.
The PMD, just for that one camera, is 160 by 120. They actually have brochures in that room over there.
So that's pretty low. I mean, you compare that to stereo, which is usually VGA at least, right? So.
Do you have generic cost relationships?
Yeah, actually, we're going to cover that at the end. Yeah, the cost. Okay, now we are going to add another dimension, 4D. Again, this dimension is also not time, something else entirely. These are brand new sensors, and they're called, you'll find out in the literature, they're called by a few different things. I guess for the purpose of this discussion, there are subtle differences between them, but for the purpose of this discussion, light field, plenoptic, or integral sensors all mean the same thing. This is an example. I hope you can see it. But there's two pictures here. On the left, you'll notice that the right, I think the car is in focus, but the flowers are out of focus, and vice versa. On the other picture, the car is out of focus and the flowers are in focus. Now, the key point here is that this is these two images are generated, reconstructed from the same raw image. Okay. And there is a company, Litro, that makes the first consumer light field camera. This is a real sexy company, gets a lot of press. I think if you ordered one in October, you're probably just getting them now. They have a 6-month back, yeah. Now, the frame resolution of these pictures are usually much lower than what you will get on a consumer camera, typically 1 to 3 megapixels. So that's Litro. There's another company that's more focused on what we're talking about here, or vision, called Raytrix. And let me just show you a video that illustrates the technology. Great. So this is a part inspection. So this is the light field camera that snapped one image, and now it's going to be moving the focus back and forth. Or you can get the whole thing in focus. So what does this give us, aside from a nice effect, is what is it, function F5, I guess? There we go. Very good. So given that we can actually infer 3D from a series and get very highly accurate and highly robust 3D from a series of these 2D pictures that are at different focuses. So you can imagine, if one pixel is getting more blurry or less blurry depending on where I'm generating it, I can get the depth out of that.
What does that do for the storage requirements?
So these are brand new. This is probably, at this point in time, is probably not suitable for embedded because of the storage requirement. It is a lot of data and a lot of processing. Nevertheless, this type of light field sensor was actually described in the early 1900s, but now we have the computational horsepower available to actually realize it. And so this company, Raytrix, they actually focus on a lot of these vision type applications for this as opposed to photography. So optical quality inspection, security monitoring, microscopy, and also 3D input, gesture recognition. So the optical train is actually quite different from traditional, did you have a question? Okay, from traditional cameras. Like I was telling Colin, you're actually sampling the radiance, the light rays, using an array of micro lenses, and I'll describe that in the next slide, as opposed to just a traditional camera where I'm just sensing just the luminance at each location. So what happens is the image reconstruction process goes through all of the processes the resulting 4D light field and generates a 2D picture out of that. Now the light field itself is digitized as a series of micro images, and this gives you the ability to do this interactive refocusing, which in turn gives us some 3D abilities. So I'll go through this pretty quickly. This on the left is a traditional camera. So we have our image plane here, and we have each pixel here is sampling the luminance from all the light rays, versus a plenoptic camera here, which is actually consists of 3 different major components: the main lens, a series of micro lenses, an array of micro lenses, and then the image plane, which actually generates all of these micro images. And in essence, that's how you're going to get a ton of these micro images, and from those micro images, you can do this interactive refocusing. So now so that completes our whirlwind tour of 2D, 3D, and 4D sensors, and actually, I did notice that I think Lytro in their next generation are going to be doing video, so that would be 5D, I guess, next. Who knows what that's going to do to the storage. So I think somebody asked about pros and cons and cost. So this is the summary. So I'll start off with 2D first. So we went over CCD and CMOS and these chip cams. CCDs typically, again, are used in scientific and industrial settings because they're higher cost, but they do give a better picture. They're more sensitive, and the noise profile is more uniform, versus CMOS, which are cheaper, but they are more sensitive to noise. But they do consume less power. So the chip cam, which is going to be found in all of your tablets and mobile devices, smartphones and such, are nicely packaged together, and they're embedded, and everything, a lot of stuff is done for you. They cost more, but again, remember that cost is offset by the fact that they include the image signal processor, the ISP, which does a lot of work to actually clean up the image, the auto gain and the autofocus and all those niceties. Then we moved on to 3D, where we talked about structured light, stereo, and time of flight. And the typical uses for structured light are industrial computer vision as well as gesture recognition because of the Kinect. For stereo, we have robotics, and for time of flight, we have robotics and automotive. Structured lighting is very simple processing, but you can't use it outdoors. Stereo is typically a low cost. You can create these pretty cheaply, but the processing load is rather high. So this kind of gets back to what Eric was talking about, where you kind of trade off on both ends of the spectrum, the processing versus what the camera can do for you. And then finally, time of flight, you have a single camera, but they have limited range, and they're also expensive. And plenoptic, typical uses, these are brand new. Pros, we saw some of that. And the cons are right now the power and then the immense processing load. But again, this is brand new stuff. Yes?
On the CCD and CMOS, what's the ratio of the price? Is it
Twice as much, you know?
I don't, Eric, do you know that?
You know, I mean, I remember in some of the stuff I've read, it's up to an order of magnitude, but that's coming down. Yeah, see, that was the problem with pricing, is just in the last 5 years, the prices are changing drastically. So it's nearly not as easy as it used to be.
It seems like there's a lot of sources, so it seems like there's enough supply out there to meet the price.
Yeah, there's enough supply out there, and then, but yeah, in terms of pricing, these things, at least up here, these things are converging, no question about it. So,
Yes?
What are some of your predictions for the impact of the Connect for Windows and its potential profile of uses for structured light,
Well, my personal, I mean, I guess my personal opinion would be that this would be, they would use this for the next generation user interface, the natural user interface. I think that's people want to maybe get, what's the next thing after touch? Maybe it's going to be, natural user interface, but that's still up in the air, right? A lot of people, there's a lot of controversy behind that.
Well, I've also seen a lot of interesting student projects with ever since they opened up the
Right.
it's doing the cool things.
Right.
Robots. I just think they're going to find a lot of things. I can't predict it, what's happening.
The Connect's been huge. Like I said, the 3D, I mean, it really has just opened up the whole world to 3D. And especially they've opened it up and it's cheap. So closing remarks, sensors are the eyes of our embedded vision system, and these sensors are improving at a increasing rate. The rate of improvement is increasing, which is a good thing. It's also, we believe it's fueled by a lot of high volume applications that are running on our mobile devices and our video games. As Jeff started this off, the choice of the sensor is absolutely hugely important to the system design and the capabilities of the system. And as well as the processing load and the type of algorithms you're going to run is extremely tied to the sensor. So we hope that this got your minds thinking a little bit about the type of next sensor you'll use or consider. Thanks. Okay, go ahead.
But so generally,
Sorry, little trigger happy.
but you're still generally talking about mostly visible light, a little bit IR, a little bit UV, but
Mostly visible light, yeah.
not radar or any other types of complementary ways of kind of getting depth or additional information blending in.
Well, I did have one bullet item about sensor fusion, but primarily, yeah, you're looking at focusing on visible light.
we did look into LiDAR, because that's also obviously very popular. LiDAR, the scanning
Okay,
laser
right.
ranging. We took that out simply because it didn't seem to fit in with everything else. But LiDAR is definitely very popular.
Stuff like seeing through walls or, I mean, the light won't penetrate,
Oh,
sorry.
yeah, the radar.
Blind kind
And
of
that's
stuff.
picked up in automotive. Radar has really gotten a lot of attention lately.
Guys, thank you very much.